but like all triangles are, is a convex polygon. It's kind of a boring example. You have like a rectangle or a square type thing. It's pretty tough to get a convex quadrilateral. In fact, I'm pretty sure it's impossible to get a convex quadrilateral. These are rather boring examples. Let's look at some more. Like we said, like an octagon, like a stop sign, octagons. Stop signs are octagons. So that's a pretty poorly drawn octagon, but it's an octagon. How about
Cool, Brett. Nobody cares.
And we'll stop at a pentagon. So we have a triangle. We have a quadrilateral, a four-sided figure, a pentagon. We have an octagon here. I'm going to draw the octagon a little bit better. So an octagon. You could get, maybe we'll even put in a hexagon. Okay. These are all examples of convex polygons, and you can make more or less, whatever. We're going to actually, we want to kind of focus our study on, if you looked at the first theorem for today is going to look at the polygon interior angles. Or how can we figure out what the sum of the interior angles of a polygon is? Well, what is the sum of, let's start with our most basic one. What's the sum of the interior angles of a triangle? 180. Okay. For a triangle, this guy is 180. Does anyone know what the sum of the interior angles of a quadrilateral is? Okay, how do we know that?
We just
As your teacher told you. Great. Okay, do we have like a more rigorous definition than that, Alyssa?
Okay, so like for the area of a triangle, it's half base times height, and it's like you put two triangles together to make like a square.
Okay, so if we divide this square into two triangles, so then if we added together all the interior angles, notice that if you add this pair together, you get this angle, this angle. So really, if we added all of the angles of this triangle together, we should get the sum of the angles of this quadrilateral. And if we have two triangles, then we should have 2 times 180 is 360. Would be the sum of the angles of this four-sided figure. Because there's 2 triangles, so we'll take 180 and multiply it by 2. How about a 5-sided figure? How are we going to figure out what the sum of the angles, the interior angles of this 5-sided convex figure is? Well, we could try this idea. What if we divided that thing into some triangles? How many triangles do we have?
5, 4.
So it should, if we draw the triangles such that they don't overlap, so that they're distinct triangles, then if we added together the angles, the interior angles, notice that if we do that, we're going to get all the interior angles of this pentagon. So we have 1, 2, 3 triangles. So the interior angles then should be, we have 180 times 3, which I believe, Brett, what did you say it was?
540.
540 degrees. What do you think the interior angle measures of a hexagon is going to be? Well, how are you going to calculate it? You could. I'd say 1, 2, 3, 4 triangles. So we could take 180 times 4. Should give us the interior angles here. How about an 8-sided figure? Anyone want to take a, without drawing triangles, want to take a wild guess as to how many? Anyone want to take a wild guess as to how many triangles I could draw without just rigorously drawing them?
10. 10. 10. 10.
How many triangles could I draw if there were 3 sides?
6.
How many triangles could I draw if there were 4 sides? How many triangles could I draw if there were 5 sides? How many triangles could I draw if there were 6 sides? So how many triangles do you think I can draw if there are 8 sides? 6 of them. If you wanted to draw them in, you 2, 3, 1, 2, 3, 4, 5, 6 triangles. The polygon interior angles theorem says is a generalization of this pattern. It says that for any convex use the term n-gon, which hopefully you're familiar with way back in chapter 1. We named polygons. N being the number of sides of our polygon. The sum of the interior angles is given by n minus 2 times 180. N being the number of sides. So let's make sure our formula works for the examples we have. If I have a triangle, it's a 3-sided figure, it's a 3-gon or a triangle. So I plug in 3, 3 minus 2 is 1, 1 times 180 is 180 degrees. Okay, it works in our first case. 4-sided figure, quadrilateral is 4 sides, 4 minus 2 is 2, 2 times 180 is 360. This is our formula we're going to use to find the sum of the interior angles of a polygon. Well, knowing that, we should be able to find the sum of the angles of any given n-gon. Just if we know how many sides, you should be able to tell me what the sum of the angles are. So like an octagon. How many sides does an octagon have?
8.
So our n, in this case, is 8. So we actually already calculated it, but we could do it again just for kicks here. You could say 8 minus 2 times 180. It would tell you the sum of the interior angles. Eight minus 2 is 6. 6 times 180 is, did someone calculate it? Did someone take their calculator at their desk? What was it, Bill?
1,080.
Okay. So 1,080 interior angles. 14-gon. So 14 minus 2 times 180, or 12 times 180 is what? 2,160 degrees, and you can calculate a 26-gon on your own. 24 times twice this, actually. So 4,320. 26-gon. Okay. If I give you an arbitrary number of sides, you could arbitrary number of sides on a convex polygon. You can plop it into our formula here and get the angle measures, the interior angle measures. And, well, with this theorem, we should be able to go backwards. So if I tell you what all the angles add up to, then we should be able to calculate how many sides there were. So, for example, if I tell you this is the degree measure, it should fit this formula. N minus 2 times 180 is equal to okay, 180, you get what? N minus 2 is that 11? Or is this 7? So N minus 2 is 7, therefore N is 9. So this was a nonagon. Well, we developed this formula based on. You can question all you want. We developed the formula We developed the formula by looking at a triangle and then building these convex polygons by like dividing into triangles. So we saw if there were 3 sides, that gives us 1 triangle. If there are 4 sides, there are 2 triangles. If there's 5 sides, there's 3 triangles. So the pattern is take the number of sides that you have and subtract 2. And that's how many triangles you can build. So if I have 3 sides, I get 1 triangle. 4 sides, I get 2 triangles. 5 sides, 3 triangles, and so on. If you haven't already, calculate how many sides this figure that has a 3,240 degree interior angle sum. Okay, 3,240, hopefully you set your problem up like this. N minus 2 times 180 is equal to 3,240. Divide by 180, and what do we get? Did you get something in the order of
18. Oh, yeah, I got 20 for my final.
24?
Oh, I got 20.
Yeah.
18 is that answer, and then
Yeah, I got that.
Oh, gotcha. Okay. That's what I get for not having this like memorized already. Okay. Sure. Divide both sides by 180. We get n minus 2 is 18. Add 2 to both sides. This is a 20 gon. I don't have one printed for this an example problem, but I'm gonna do one real quick with you. Kind of an extension of this that you'll see in your homework tonight is looking at what's called a regular polygon. What's special about a regular polygon? Do you remember? All the sides and all the angles, all the interior angles are equal. That's not wrong. Okay, so we can, as an extension of this, I could say a regular polygon has a 144 degree interior angle. How many sides does it have? A regular polygon has a 144 degree interior angle. How many sides does this thing have? It is possible. Well, let's think about this. So, if it has a 144 degree interior angle, one of them is 144 degrees. Well, how would we find the sum of the angles? Let's think of, so what I'm getting at is let's come up with 2 different ways to calculate the sum of the angles of this regular polygon. Okay. Well, one way to do this, one way to find the sum of the angles would be to go with our formula from before. However many sides it has, take away 2 times 180 has got to be the sum of the interior angles of my polygon. The issue is I don't know what this is equal to. But we can come up with another expression that would give us that. What would be another way? And the key here is that we know that it's regular. Okay, so think back to what does it mean to be regular? Hopefully applying to angles. So you know all of the interior angles are the same measure. Okay? What is the measure of any one of them? 144. Okay? How many angles are we going to have? We don't know. But what's the expression that would tell us? If you have a triangle that has 3 sides, how many interior angles does it have? 3. A quadrilateral has 4 sides, how many interior angles does it have? So the number of sides equals the number of interior angles. So if n is the number of interior angles, and all of them are the same, if I just added together that same thing n number of times, I would get another expression for the sum of my interior angles, of my regular polygon. So this should be equal to the measure of one of the angles times how many sides there are. In this case, there are n sides. Oh boy. Well, what could we do to solve this? Once you're here, now it's a nice little algebra problem. Distribute out. You get 180n minus 360 is equal to 144 times n. You can subtract 180n from both sides. And you end up with we end up with what? Negative 360 is equal to negative 36 n. So what's n equal? This is a decagon. Therefore, n, or the number of sides, is 10. Or this figure, this regular figure must have been in the decagon, a 10-sided figure. You'll see a couple of those in your homework. Okay. So back on track. If I give you a diagram with some missing angles, we should be able to find some values of x. So our strategy, if I ask you to give you the interior angles of a convex polygon, your strategy should be, let's figure out what the sum needs to be based on the number of sides, and then we'll create an equation based on the angle measures that I give you. So, like, for example, what should the sum of this interior angles of this first figure add up to? It's a 4-sided figure. 4 minus 2 is 2. 2 times 180 is 360. 360 should be equal to add the sum of each interior angle. So if I add up the 4 interior angles, that should add up to 360. So 72 plus 108 plus x plus 87 should be an equation that I could use to find this missing angle measure. Okay. I add together the 4 interior angles. And that should add up to the sum, which I got from knowing this is a 4-sided figure. Add them together and you get, what, 180. So x better be 93. What should my equation look like in the second figure? Count the sides. Ben, what'd you get? 7 sides? 1, 2, 3, 7. So the sum, this should be what? 7 minus 2 times 180. And that should be equal to the sum of each of these. So we can add together all these things. So x plus 2x plus 6 plus 133 plus 99 plus 112 plus 145. 7 of them. Okay. Combine like terms, you get a 3x here, and then these things use a calculator to add together. You have 5 times 180 is 7,000? 700? 700 for me? Is that less? Am I off? Way off.
I got
900. Yeah, sorry, 900. What do you get for doing math? 900 is equal to what? 3x plus. Did someone take the calculator and add 156? What do we get here?
645.
Okay. Subtract and solve. And what do we get for x? Solve. What do you guys get for x? I don't know off the top of my head. I'm relying on you guys to be able to subtract 906 of this and divide by 3.
Oh, wait. Yeah, I have to do divide by 3.
85. Perfect. So those are exterior. Those are interior angles. Excuse me. The interior angles of a polygon varies with the number of sides. More sides, a larger sum of the angles. Okay. What would you expect? So, what would you expect the sum of the angles? This might be like a higher order thing here. But what would you expect the sum of the interior angles of a polygon do as the number of sides gets really big? Like say tending toward like infinity. Like you get more and more sides. Would you expect? What would you? Okay, so the polygons will look more and more like a circle. And what would you think the sum of the interior angles is going to do? The interior angles. Notice are these increasing? Are they staying the same? Are they getting smaller? The sum is getting a lot bigger. The sum is increasing. So actually, as we get more and more and more sides, your sum of the interior angles is going to explode. It's going to get close to. I mean, it's going to approach, if not hit, as close to infinity as you can get. What's awesome is that the exterior angles does something completely different. If we look at the exterior angles of a polygon, or most specifically the exterior angles going in, say, one direction. So recall that the exterior angles of any polygon we get by extending a side between a side and a side extended. So we can actually create exterior angles of a polygon by extending each of the sides, and then we can work around, say, in one direction. Notice that exterior angle, exterior angle, exterior angle, exterior angle. Of a triangle, recall we had a nice theorem that said like what any one exterior angle is. Do you remember the exterior angle theorem for a triangle? Yeah, it's any exterior angle is equal to the sum of the opposite, the alternate interior angles. Way back there. What's kind of cool is that the exterior angles of a polygon, no matter how many sides we get, if you add them all together, we actually get a constant number. The polygon exterior angles theorem says that the sum of the exterior angles of any convex polygon and we'll look at just one per vertex. So you can actually make 2 exterior angles per vertex. We're going to go with just one. If you add up one exterior angle per vertex of a polygon, it's always constantly 360. One per vertex. So unlike the interior angles, whereas we keep adding sides, then the sum kind of explodes out to infinity. It just gets bigger and bigger and bigger and bigger. If we keep adding sides to if we keep adding sides to a polygon, the sum of all the exterior angles actually is always 360, no matter how many sides you get. So if you have a triangle, the sum of the exterior angles is 360. If you have a quadrilateral, it's still 360. If it's a hexagon, it's still 360. If it's a 2000 gon, it's still 360, assuming we only measure one per vertex, which is kind of astounding, actually. Kind of cool. So, for example, I have a couple guys on here. Notice these are all exterior angles of my polygon here. In this case, it's triangle. One per vertex, created by extending the sides. Extending a side and measuring the side and side extended. So if I add these together, the exterior angles theorem says that these angles added together must always be 360, or 152 plus 137 plus x is 360, no matter what.
Is that just a triangle?
And this is true for any polygon. So even if this pentagon, if I add up all the exterior angles, one per vertex, they're still constantly 360. So x plus 67 equals 360. You can solve for x. So let's think about this. I want you to think about this a little bit more. Let's extend this idea. So if the sum of the exterior angles is always 360 no matter what would you expect the size of any one exterior angle to do as you keep adding sides? What would you think what should happen to any one given exterior angle of a polygon if you add more sides? Okay? What's it? Decrease. It has to. The more sides you add, you'd think that the size of the exterior angles actually should shrink. It has to go down because if you keep adding angles, you keep adding up a bunch of numbers, and they stay at the same. That means every individual piece must get smaller as the number of sides gets added. Just kind of cool. In particular, if you define a circle, if you define a circle to be like sometimes you can define a circle to be an infinitely sided polygon. Just add little minuscule pieces. Then you'd think that the exterior angles of a circle should always be essentially 0. Let's approach that. It's kind of a weird limiting case. But anyways, just something to keep in mind. Interior, exterior angles. Any questions?